I'm going to solve a capacity problem, which is not very straightforward. Not that it is difficult, not at all, but it is not similar to what I have solved in class. As I explained to you many times, it really doesn't matter if I solve 100 problems in class and you copy them and you learn them and you get 100. It doesn't matter because the problems that you will encounter in reality will be very different than the problems that I have solved in class. You really need to develop creativity capabilities to be better prepared for, 40, 50, 60, 70 years of useful working life. As I have explained many times, you are under several threats. The first one is climate change. The second one is viral attacks, which unfortunately we see how serious they can be. And the third one is the marriage between biotech and infotech, because given this integration of these two capabilities, you may live for 100 years or even more, and you may need to work for 70 years or even more. During these years, you should have the capabilities of reinventing yourself to be able to work in this ever-changing environment. And the last difficulty is professors who are businessmen or business person. They care about other things rather than how much their students learn. I hope I'm not among them. So let's go and look at this problem and see whether we had enough knowledge to be able to solve this problem or not. This is the problem we have. I show you the preview. This is the situation. Applicants come into a local department of motor vehicle. A percentages of them are directly sent to the station or the resource which issues license. A percentage go to eye test. Out of that percentage who go to eye exam or eye test, a percentage are rejected and leave from the beginning also a percentage are sent to written test. And out of these people who get accepted in eye exam, a portion of them also come to written test. And those who fail in the written test, they leave, and then the rest go to the last session to issue the license. For resources, number of resource unit here is 1, here is 1, here is 3, and here is 6. Unit load at each of these stations is 0.8 minutes here, 6 minutes here, 16 minutes here, and 5 minutes over there. The problem asks for capacity of these stations. That is quite straightforward. So I get a picture of this part. Reception, eye exam, multiple choice, final. These are what I have. 1, 1, 3, 6, 1, 1, 3, 6. And that is number of resources, which we show it by C. 0.8, 6, 16, and 5. And these are unit loads, or what TP. RP capacity per minute, I have 1 minute, and every 0.8 minutes, I can handle one applicant. Therefore, I divide it by this one, and the capacity is 1.25. Here, I have one resource. So in each minute, that resource has 1 minute time, and it takes 6 minutes to complete the work of an applicant in the eye exam. So that is 1 divided by 6. Therefore, every minute I can handle 0.16667. I copy this down, but here I don't have just one resource. I have 3 resources. So that is C divided by TP. And instead of 3, I simply click on this. And then when I copy it down, I have the capacity for the last resource. Here, if you want to see the formula, these are the formulas which I used over there. That is capacity per minute. If I want capacity per hour, that is simply 60, because an hour is 60 minutes, and I multiply it by this, and then I copy it down. The minimum of these 4 numbers, which is this one, has the lowest capacity, not for this total system, but for that station only. And I will later explain what do I mean by total system or by that specific activity or resource. So these are the capacity of these 4 stations: 75, 10, 11.25, and 72. The next question is, what is the utilization of each of these resources and resource pools? We need to find throughput. Computation of throughput is a little bit difficult for each station, and I will explain. The first thing we know is 22 applicants come into this system. So I go over there and I type 22. This is throughput to the whole system. Out of those, 50% go directly to the last step, and 20% go to multiple choice, and 30% go to eye exam. 50%, 0.5, eye exam 0.3, and multiple choice 0.2. And the summation is equal to 1. But out of those people who go to eye exam, 80% pass it and 20% do not pass it. This will be equal to 0.8 multiplied by 30. So this much will be accepted, and then they should go to multiple choice. Therefore, here that 20% were coming from there. The total which goes to multiple choice is equal to summation of these two into multiple choice. So what goes to I would be 0.3. Out of those people who go through the multiple choice, 10% of them fail. So 90% would be accepted, multiplied by this percentage, which is 0.396. And these people will go to final, and final will be composed of those 50% who went initially plus this percentage which go through multiple choice. Therefore, in general, in the final stage, I have this many. This is final stage. 89.6%. 100%, they go over there. People who go to eye exam are 30%, 0.3. And therefore 0.2 also is here, and 0.5 will go there. Out of people who take the eye exam, 80% of them pass. So that is 0.8 times 0.3 is 0.24. 0.24 is here, and here was 0.2. So together, when they pass here, is 0.2 plus 0.24. They come out. But out of this, 10% fail, so only 90% of them will go. Therefore, 0.44 multiplied by 0.9 is equal to 0.9. Now, if you go up and if you look, I have 3.96 here. I have 0.3 over there, and I have 0.896 over here. Those are percentages. Therefore, now if I'm going to compute throughput, it would be equal to this one multiplied by throughput, which was here, and log it. 30% goes to iExam. Out of those people who go to iExam, 20% of them fail. Therefore, this much of them will pass, and 20% go to multiple choice. So summation of these two will go to multiple choice. And then out of those who go to multiple choice, 10% of them fail, and the rest will be added. This is 90% of that, which is here. And that would be added to the original 50%, which makes it this. Now, if I copy this one and this one and this one down, each of them all multiplied by that throughput. Now, utilization is equal to throughput divided by capacity. That is throughput per hour. This is capacity per hour. These are the numbers that I have: 29, 66, 86, 27. 29, 66, 86, 27, 86, and 27. These are utilizations. Now, let's go to the last part. Compute the capacity of this system. What is capacity of this system? Utilization of this station now is 29%. While we have 22 people coming into this system, utilization is 29%. Out of each person who comes into this system, 100% of it goes over there. 22 people only require 29% of that capacity. Capacity of this one, it can handle 33 incoming. Don't forget, capacity of this is 10 per hour. How with 10 per hour it can handle 33 per hour? Because not all of them go to this station. The same is for this one. Capacity of this station is 11.25 per hour, but it can handle 25.5. Capacity is 11.25 per hour, but it can handle 25.56 per hour. Because not all of them go there, and the last station can handle 80. While the capacity is 72, it can handle 80 per hour because not 100% of customers will go there. Now, out of these four numbers, which one is the lowest? 25.56. What is the bottleneck? 25.57. If you double this capacity, if instead of 3, if I put 6, double it, this one will go to 51, but the bottleneck now shifts over there. Capacity of the bottleneck is 33, and therefore the answer here is 33. Also, there is one other way, indeed more than one other way, to solve the last two parts, which are the most difficult parts. Look at here, look at the simple part of the problem, which was here. We had TP and we had C and we computed capacity. Let's do the same thing with one difference. We know that each unit which goes over there, that resource will spend 0.8 minutes on it. And all resources go there. Therefore, the time that it will spend on each incoming applicant is this one multiplied by this one. This is new TP. Let's call it TP prime. Each unit which goes into the eye exam, there will be 6 minutes spent on it. But not all units will go to eye exam. Indeed, only 30% of units go into eye exam. Therefore, we can say for each new person who comes into the system, which not necessarily goes into eye exam, for each person who comes here, in eye exam, we will not spend 6 minutes, but we will spend 6 minutes multiplied by 0.3, because only 30% of people go there. Therefore, if I copy this down, this is the new TP for eye. For each person who enters the total system, not who enters the eye exam, for any person who enters the total system, the time that we will spend on that person in eye exam is 1.8, because 30% of that person will go to eye exam and 30% of 6 is 1.8. The same is for multiple choice. Every person who goes to multiple choice exam, there will be 60 minutes for that person, but not everyone goes there. Indeed, out of each person who comes into this system, only 0.44 of them go there. Therefore, the time that we will spend on each individual which comes into the system, not each individual who takes that exam, is 0.44 times 16. And finally, for the last part, each person who goes to the last part, 5 minutes order. But not everyone goes there. 0.896 go there. Therefore, for each person who comes into this total system, that person which may not go through the last stage will be in the last stage 4.48 on average. So these are TPs. Now replace these yellows by these greens, where the rest remains the same. Look what you did here. You came and said equal to divided by TP, and then we copy it down. These numbers are similar to these numbers, but have been computed for T prime instead of TP. Now, if I multiply each of these by 60, then I get the capacity of each station in terms of the number of people who come into the total system, not the number of people who come to that station. Now, if I type, is this equal to this? Yes, true, true, true. Not true, but it is indeed true, because if I add to the decimal point of this one, look, they are very similar, but maybe a very small difference is there. Equal to this one minus this one. It is almost zero, a little bit difference. So this is a second way. You may benefit from your own creativity and find other solutions too. My friends, I really understand that this was not a very simple question. The first part were extremely simple, so you should have got 40 over there. Out of the utilizations, at least you should have got half of this. Therefore, for a person who has studied a little bit, you should have got 60. And then out of the next two, if you have answered one, you would have become 70, and that would be a C. If you are looking for B, you should have been able to compute all utilizations. But if you are 80, you still are very good. If you are 100, you are perfect. I mean, if in this quiz, only based on your own capabilities, if you got 100, I really like to shake your hand. I really like to appreciate you with all elements of my value system, because while you have paid not that much money for your tuition, you have tried to collect knowledge as good as Stanford, Berkeley, and whatsoever. So I really thank you for understanding this. And if it was a little bit difficult, I recommend you to watch the solution that I have made again. In exam, you will see problems easier than this. Frankly, I gave you this quiz to measure creativity of the class. So if you have not got 100, I will not be worried. Still, you may get 100 in the course. Thank you very much. Thank you for your attention.